Just a couple of announcements. We're going to start from scratch. Last week, I think we progressed a little bit, and then we had our technical difficulties. But today we're going to start again on part 1 of 2 for the design of a two-way post-tension slab in ADAPT Builder. And we will record today's meeting. We're going to place the recording on our YouTube channel, which is on at www.youtube.com/adapt-support. There's a webinars playlist that you can go ahead and access. I will have all of the different webinars in that particular playlist. And also, we want to make sure we're going to reserve question and answer for the last part of today's meeting. We're going to go about an hour and then we'll stop. We'll have 10 to 15 minutes for Q&A. I will ask, I'm going to mute everyone's microphone just in case there's any background noise, so it doesn't disturb the meeting. So I'll go ahead and do that. And then if you do have questions that are specific maybe to something in the training, you can always access the chat box to ask the question. But we would prefer, if you don't mind, just reserving questions until the last part of today's meeting. So hopefully everyone can hear me. If you cannot, please let me know and we will go ahead and continue. So today we're going to work again on part 1. We're going to talk about building the model from a Revit file. We're going to talk about importing the Revit model to ADAPT Builder. Also, how do we convert a CAD file to an ADAPT Builder model? Some of these are pretty basic steps in the process, but the training is really for beginner to intermediate type level users. So we're going to start with the Revit model. I'll go ahead and inside of our Revit window, we should have the Adapt tools under the Analyze ribbon. So in the Analyze ribbon, there's this Adapt section. This is installed in Revit per the ADAPT-Revit link, and we have links stretching all the way back from Revit 2019 back to 2008 or 7, somewhere in that region. So we have several years worth of Revit links. This being the latest, we are working on Revit 2020 link now, which we should release when we release Builder 2019 later this summer. So we're going to use the option to export the Revit model. Now in the Revit model, a couple of important points to point out here is that the Revit model must contain structurally enabled components. So if you select a slab region, for example, this slab region is structurally enabled. You have to have a material assignment as concrete assigned to the component for it to be interpreted by our IMP extract. We access the Revit API, and we're looking for certain things when we extract and write the data. This file gets written to an IMP format, which is what ADAPT uses for integrating with Revit, eTabs, Tekla Structural Designer, any builder-to-builder models that you want to interchange within the Builder platform, ADAPT's own platform, you would use IMP also. So this is a pretty standardized format that we use for extraction and then importing into Builder. So we'll go ahead and we'll say export. We want to export this model. The first dialog that will appear will be an option that is used to map default column parameters to user-defined or custom parameters. In this case, we're just using the default column parameters. We'll go ahead and say OK. And this dialog for the ADAPT-Revit link is read-only. The only real true selection you can make is how we access and what levels we access to export from Revit to ADAPT. In this case, none means you're basically importing everything. Any level that is assigned in Revit will be imported into ADAPT. In some cases, you may not want every single level because that means that anytime you model, for example, a wall or a column in ADAPT, in order for the column to be extrapolated vertically into a stack, you have to have a column that spans, let's say, every level. So if you have a level that's 2 inches high, there's a column that becomes 2 inches high, and that becomes a little bit cumbersome to deal with. So our recommendation is to use active. Active will import only the levels that structural components are assigned to in terms of their position, so in the Revit model. So if you have non-structural components that are attached to non-structural levels, they won't be included in this active selection. The structural selection means that any level that is tagged and assigned as structural in Revit would be exported to ADAPT. So in this case, we don't have any structural levels assigned, so we'll use active. And you also have a dialog which shows just the component count of items that will be imported, or rather written to the IMP file, load cases, and load combinations. In this case, I'm going to select my load combos, and I'll leave those inside of Revit. We'll build those out inside of the ADAPT model, and I'll go ahead and export that. We'll save this as an IMP file, and that process is done. I'll just set Revit to the side, and I'm now going to import this file from Revit to Builder. So I'll go to File. Actually, let me back up just one step. I'm going to launch Builder. Today we're using Builder 2018 Build 2, and this will be distributed actually today to users who are actively using Builder. This was prepared on Friday of last week, and there's a few minor fixes that were made between Build 1 and Build 2. Mainly being able to view crack deflections inside the main viewer, and also being able to view long-term deflections along support lines. So those are the two main fixes for this particular build. So inside of Builder, we're going to select Floor Pro. Floor Pro is the main module that we'll be using to design the two-way slab. This allows us to design two-way slabs, beams, one-way slabs, and we're going to select the option for PTRC. That gives us the ability to model the post-tensioning. Edge is not technically required for this particular webinar or the webinar that will be held on Thursday. We're going to be working in single level mode, just doing a single level in isolation. Even though we might import the entire building, we're only going to work on one level. So I'll turn edge off for this instance. And inside of Builder 2018, we'll go directly to File, and I will choose to import the IMP file that we created from the Revit link. And we'll go ahead and navigate to that file. We called it Revit to Adapt 1. And inside of Adapt Builder, we now have a dialog that has the ability to interact with the user, meaning the user can make some selections here on what they want to import into the structure. So first thing, by default, the program will select the option to create a new model, and we're going to create everything. So if we select OK, the program will build a full model based on what was modeled inside of Revit. You also have the ability, notice that here the components, when you import an entirely brand new model, these are all grayed out because we're just building a new model. We don't really require the ability to filter the component that we want to import into the Builder workspace. If you want to import a single level, you can choose a level from this pull down list. For example, if I want to import level 3, which was defined in Revit, I import that in my reference plane that I'm active on currently in Builder, which is the default, is called current plane. This is the first elevated plane in Builder. And if I was to draw these planes, we have current plane, top plane, and then we have bottom plane. So if I import level 3, this will basically come in here to current plane. If there are columns above and below, obviously those will be above and below, or vice versa. So this is how you can import one level. And when you go into that mode of importing one level, then you have the ability to filter out components that might be imported: beams, columns, walls, slabs, and so on. the merge similar slabs during import, this will basically combine slabs of the same thickness and the same offset. So if you have multiple slabs that could technically be merged into one slab to simplify the geometry, this is used for that purpose, for this merge setting. We're going to import everything, so I'll go back to all. And if you wanted, by the way, to update a level, maybe you already have a level that's been built and something was updated, maybe the columns changed. So let's assume you had already previously imported a model from Revit, you built a model, you have the post-tensioning in the model, and you're going through that design process, and then all of a sudden a few of the columns change, which happens pretty frequently, I would suppose. You have to have some way of being able to update those columns in the existing model. So in that case, what we would do is we would choose to update the specific level that we have already created, and prior to importing the columns, we want to delete all the columns in the existing model. And then we'll come here, and let's say we only want to import the columns. I'll deselect everything, select only the columns, and I re-import just that selection. So that's a way to, let's say, replace components that may have changed as a group from a different updated model, Revit model. Okay, we'll go back and import everything. Load cases and load combos. Oftentimes these are not, basically these are blank for a Revit model. If we're working with ETABS, it's more common to have load cases and combinations that we might want to import from, say, ETABS to ADAPT. So we'll go ahead and select OK, and the program will build the Revit file. So it's important to note kind of what mode of operation we're working in when we get this imported into Builder. Right now, if I use my viewing tools here, there's some quick access tools at the bottom and also up here at the top. These are more functionally related to just program operation. These are specific to, let's say, modeling down at the bottom. And if we go to the top view versus side view versus 3D view, let me go to a side view, you can see this imports the entire stack of levels. And we're working in what we call multi-level mode. At the top right, you switch between multi-level and between single level. So immediately we recognize, okay, we want to be able to only analyze and design in single level. We're just going to work on level 3 for this webinar. So I can immediately go to single level and navigate to the level in question. So this is level 3. Now we're just seeing the extent of the immediate levels above and below level 3. Level 4 and level 2. The active level that we're working on is highlighted here as level 3. I'll go back to a plan view. By the way, you'll notice if I am in multi-level mode and I try to mesh the structure, if I go to analysis and I go to mesh, it's inactive. It's inactive because we have opened the program without edge, so we don't have the ability to even mesh or analyze in this particular multi-level mode based on the settings we made when we entered the program. If I go back to single level, then these become active. So the program will kind of filter what tools are available depending on what modes you select in the splash screen when you enter the program. Okay, so we're going to put this to the side. We'll go through and set up our criteria and further work required for this evaluation. I'm just going to save this quickly. Let's save this model. And I'll just call this model 1 from Revit. I'm going to go ahead and start a new file, and we want to show the operations for transforming a CAD file to ADAPT. All right, so we'll go to File, and we have a CAD file. The most important thing is if you want this process to go faster, then we recommend you model your components in CAD as polygons, poly regions. That allows us to quickly transform those polygons to components inside of ADAPT. If they're not transformed, you can still build the model from CAD, but it becomes a little more time consuming, and you have to jump through a few extra hoops to get what you want in terms of the modeling. So we're going to import a DWG file, and we'll use, this is levels 1 through 3. This is typical of those particular levels. Within the conversion process, we have to calibrate the file. That's usually required. You can post calibrate. If you go to the home menu, there's an option actually to calibrate after the fact if you forget to do so. But we'll do it initially here. We'll calibrate the file. We can also move the file into an origin, XY position. This might be more important if you have, let's say, a 20-story building and you have unique CAD files for every level. You have 20 CAD files that you want to import. You might want to import those and assign them to different levels vertically in the building, but you want to have the right anchor point, the right origin for each one of those levels. In addition, you can also insert a CAD file to a specific position vertically. So if I'm working here in a model that I've already assigned all 20 levels, I can go ahead and select the level I want to assign the CAD file to using this pull down. So these two options are not really required for what we're working on here. We'll just calibrate, and I'll just call this model 1. That CAD file actually gets stored in the group library. If you go to visibility, group library, it's stored there. We can turn it off and on from that location, so we'll show that. It's asking us now to enter the start point of the calibration. So we're going to use just this dimension from grid A to B as 20 feet. The snap tools are locked at the bottom center, so I'll turn on snap to endpoint to be able to click on that endpoint of that line to this line, and we'll go ahead now and say this is 20 feet, and then I will use zoom extents down on the bottom. Also, these tools for viewing can also be acquired here under home, zoom camera. So there's a set of tools there that has more predefined viewing selections for your model. Okay, so now we're going to convert this to structural components. Right now it's just a flattened CAD file. There's no vertical dimension to anything. It's just a 2D file, and we want to be able to convert it and provide components for the model. So I'll select, let's say, the slab polygons first. Notice if I select that slab edge, I'm trying to select this balcony, it selects the grid line. And I say, well, that's not good. I want to select the polygon. And again, it continues to select the grid line. So if you press on it once and press tab, it will actually toggle between the two. So there's the polygon, and then I'll press control and select the other polygon, and now I have 2 items selected. We're going to be working in the model ribbon mainly. So under model, we'll go all the way over to the right. There's this transform panel. This is strictly used to transform polygons to components, so I'll transform those to slabs. Notice when the slab is created, it's turned green. That's the default color for the slab. I'll select my walls. So we have, I think, 5 walls in this model. There's 3 here. There's 1 there and 1 over here. And we're going to use transform single walls. Now, if this H-shaped wall group was like one complete polygon, we would use the option to transform a compound wall. But here they're individual regions, so we can use this first option here. I'm also going to select my columns. Now, if I window select, if I just sweep window this and I go and transform columns, this is not a smart thing for me to do because it's going to try to transform other closed regions as a column. So I want to isolate the layer that is truly representing the columns, and if I double click on that polygon, it will open a property window. This is called tutorial level 1 column. So what I'll do is use the layer settings to isolate that layer and then window select. Or alternately, I could click 1, press Control, click 2. That takes a long time to do, especially in a large model. So we're going to go back to Home, and there's this option for layer settings. Notice it's also a quick access option down here on the bottom. I circled that in blue. So if we go to layer settings, I'll turn all of my layers off, and I'm going to find the column layer for this set of columns, and I've identified it. I'll turn it on, and now I can just window select. Going back to the model ribbon, I want to transform those into columns. Okay, so once I've isolated and transformed, I want to go back to my default display. And my default display is under the visibility ribbon. This default display is actually stored in view settings. So view settings is what we would consider like the main control panel for visibility in the program. If you ever get stuck, if you ever are trying to turn something off or on and you don't know where all the quick viewing off-on tools are, you can always come to this dialog and control the visibility for anything. And you can also save the group of settings as the default. In our case, our default shows all structural components. So notice we have our slabs, our columns, walls, and balcony slab. My CAD file was turned off because when I went to layer settings, I turned that off completely. So I want to go ahead and turn it on. Now it's not as efficient to try to sift through these and turn these on. I could say all layers on, that's one method. And now I get my CAD file back on because it was part of the selection for all of my layers that I turned on. If I go back and turn all those off, I'll kind of get back to the state we were just at. I can also go to visibility. And remember that the CAD file is stored as a group, so I'll turn this on here. Okay, so this is an alternate way of doing that. There's one more thing we need to transform, and that's just a couple of openings here. So we'll go ahead and transform openings. And I'll turn my CAD file off. So we have our model in place. If I go to a side view, I might want to copy these columns and walls vertically. So I don't have to go to a side view to select them. I could take more time and press Control and select them this way, and that again is less efficient to do it this way. Or you can go to Home, and we're going to select components by type. So here we could select all of our columns and walls. And I'm going to go back to this view because we can see it very cleanly here. If we go to Modify and we copy and move vertically, we're going to copy those up one time. So we copy those up to this level. Okay, so this is now the model by importing a CAD file and only having one level assigned. If we go to multi-level mode, you can see that I'm also going to turn on the reference plane tags there. So you can see in multi-level mode we have current plane, top, and bottom. If we compare that to the other model, we had all of our levels. We're going to use the model here to continue with the training for this webinar. So I'll go ahead and save this model. Call it Model 1 from CAD. Okay, so we've talked about generation of the model. We're now going to add some loads, define the combinations, and look at some of the design criteria. First thing we want to do is define just some loads on the slab. We're not going to get too involved with loads. Notice that this slab by default is an 8-inch slab. It's referenced from the current plane, and there's a 0-inch offset. So if you want to offset a slab downward, you would input a positive number here. If upward would be a negative number. This particular slab here, which is our balcony, we're going to say is 7 inches, and this is going to be an offset of 1 inch there. If we want to confirm geometry for any model that you're working on, you can use this section cut tool. And this section cut tool allows you to click on a couple of points. Maybe we go from point 1 down to point 2, and then we click an insertion point, and this will show us the cut through those 2 points. You can see there's the balcony step in right there. So this is a nice handy tool to confirm geometry in the model. Let's delete that. We want to assign loads. Loads in the program are always superimposed. They're additive. You can assign both positive and negative loads, meaning positive and negative global direction. So for a gravity load in the positive direction, it would be along the z-axis. For a negative load, it would be upward along the z-axis. We'll go over to loading. For load cases, we're going to primarily be working in general loads, gravity / lateral. The lateral here can be a little bit misleading. This is really lateral loads that are placed on the slab as reactions from a different structure. So let's say it's a podium slab where you have a timber structure bearing on a gravity podium or transfer slab. All of the reactions that are defined on the concrete podium slab from the timber structure need to be assigned as general loads, gravity / lateral. The building loads option here will not be used in single level mode. These are only solved for in global mode. We're not going to be running global mode for this case, and this more represents a full set of lateral loads, seismic or wind, let's say, that would be applied to a global structure. So if we had a 20-story structure, and we might need to figure out what the distribution of story forces are for wind or seismic. Based on our wind and seismic wizards, the program would generate these loads and then apply them to each level based on this distribution. These would then be automatically classified as building loads. So we're going to be working in this realm today. We have a few other webinars that will tackle the issue of building loads and how they're defined and processed in the program. So the load cases that we're going to be looking at are dead load. This is really superimposed dead load, live load, and also pre-stressing. That's checked up here as well. Once we add tendons, it automatically engages this load case pre-stressing. One thing that's important to note is when we check load balancing for the post-tension design, the program automatically considers, let's say, the ratio of the PT, let's say uplift divided by the sum of dead load plus self-weight. So if you assign load to this load case, dead load, let's assume again it's superimposed. If you do not want that to be included for the balanced loading check, then what we need to do is basically abandon this and write in a new a new load case and assign the superimposed dead load to the new load case. In that case, the program would only check load balancing on the self-weight, not the self-weight plus the dead load. So we could always add additional load cases here and rename them. This might be called SDL, for example. The live load in this case is not reduced currently. So this reducible option, if I tag this live load as reducible, this is only used for load takedown for a multi-story building and also for column design. So it doesn't really apply to the horizontal live load reduction for a floor. We can use load patterns to do that reduction. We're going to ignore that for this training. We're just going to assign the full unreduced live load and then the superimposed dead load. The program will automatically calculate the self-weight of the structure. We'll go ahead and select two regions. So anytime you select a slab, if you use the wizard, we have a line load wizard and also a patch load wizard. The program will map load to the selected slab. If you use the regular option, line and point load, line load requires you to input 2 points to define the path of the load. Patch load requires you to input at least 3 points to define the polygon where the patch load will be placed. These two options will do this automatically. So I'll use patch load wizard. The dead load we're going to assume is 0.02 KSF. This is still selected, so I can go immediately back, and we'll assign this as let's say 50 PSF or 0.05 KSF. Note that every load is its own entity. When you define a load, it only represents one load case and one magnitude. It cannot define 2 load cases. So notice I had to run the operation 2 times to get load assigned to dead load and then load assigned to live load. I'll go ahead and use the line load wizard to define, I'll just say it's 350 pounds per foot of line load. Now when I add loads to the structure, those are shown visibly. I'll go ahead and rotate this to 3D, and those are the loads. In the latest version 2018.1, there's a new panel for those of you who've used this software and who are using it currently. There's this panel which makes it easier to manage the visibility of the loads. You can show all loads. Okay, you can isolate load types, point, line, and patch. So these are the line loads, patch loads. It shows everything. If you want to drill down further, then you can use the load settings, which allows you to turn off certain load types, dead, live, super dead, whatever other load types you have classified. And then you can also access the graphical reporting mode and even RTF or XLS reports for loads using this last button. So this gives you more of a abbreviated way of getting to view loads versus what was going on in the past versions of the program. Okay, I'll turn all loads off. And let me go ahead and save the model. We're now going to look at criteria. So we'll go over here to criteria. And for concrete, I'm going to go ahead and add a concrete. We're going to call this 5,000 PSI. And I'll go ahead and update the values here. The modulus of elasticity will update automatically based on this input and based on this unit weight or density of the concrete. You can add multiple load cases, material assignments in this dialog. We'll say OK. Now, in this case, we're going to assign everything to concrete to 5,000 PSI. So I'll select everything. I'll go to modify selection. Whenever we modify more than one component, we use modify selection. If I say item properties, that only modifies the first selected item in the group. Okay, so this is actually modifying just wall number 1 instead of everything. So again, we need to use modify selection, and we're going to go to material, and we'll change this to 5,000 PSI. Okay, so I'll go ahead and say OK. We've modified the geometry or the criteria for the concrete. Rebar, we can make rebar selections in terms of the material here. I'm going to change the modulus of the rebar to 29,000. Pre-stressing, I'll change the modulus of the PT steel to 28,500. Steel fiber and generic materials, these are not applicable to what we're doing. I'll leave those alone. Design code, this will basically set the design requirements both for serviceability, minimum reinforcement, and also for design of ultimate level forces, moments, tension, etc. for the sections. So this is important to define the proper design code. In this case, I'll use ACI 14. Once we actually switch that if I come out of that and I go back to loading, load combos, this will basically be reset. So these are the default combinations that we write into the default settings of the program. The user can select and choose to set any model as a template. Okay, so if you write in 200 combinations in here and you want to save that as a template, you can always save that particular file as a project template, and it allows you to save the criteria settings, the material settings, and the load combos. This is a way to save time if you're using the same combinations over and over and over again. You can also choose to import files or import load combinations from an IMP file. So for example, I may not want to key in 200 combinations that include wind and seismic for a multi-story model. So I can always go and choose an IMP file of a model that has already been created and use that as my load combos to be built into this model. So I'll go and use master loading ACI. I'm going to update my model. I don't want to create a new model, and I'll deselect all of the components. All I'm really interested in is the set of load combinations, and I'll import all of my combos from the IMP file that I've created from a different model. And I can say, okay, this is just a warning saying, hey, you already have initial in your current model. Do you want to replace it? And I'll say, yeah, I'll replace initial. And we can see there is a load combination list here. This takes a little while to open, but you can see this has, what, 241 combos that were imported in from that model. This includes wind, seismic, and multiple gravity loads, dead, snow, live roof, and live load, I think, in this model. And once I import this, I can now save this as a template that includes these combos. Okay, so we're really only focused on gravity combinations today, so I'm going to go back to the basic set of default combinations, and I'll do this by selecting criteria. I actually accidentally selected load combos. I'll cancel out of that. Criteria, design code, and I'm just going to toggle back between ACI 11, that resets it, and come back to 14, and I basically just dumped all those combinations, flushed them out of the model. So we're going to work primarily off of this set of combinations. Now, before we continue, we want to talk about how does the program handle these load combination types, and then how do we go ahead about introducing crack deflections and long-term deflections. So for service combinations, the program will report stresses. For example, we want to know what the top and bottom fiber stress are in the slab for design for the PT. The program will report those for service classified combos. It will also report pre-compression and balanced loading. It will design reinforcement for minimum requirements for these load combinations service. For strength, the program will design reinforcement for whatever ultimate factored level forces are produced by that combo. So if you have a moment at one particular location along a strip in the slab of 500 kip feet, the program will add rebar necessary to meet that demand along that support line and strip. So this is for factored level ULS, ultimate limit state, consideration. Initial is kind of a specialized check for PT that we might want to make, where the program will design, it will check, not only check stresses at the initial condition where we transfer the post-tensioning force into the slab, but it will also add reinforcement if the initial stress exceeds a threshold governed by the code. And so this particular combo could potentially require reinforcement, whereas for ACI, this combination would require reinforcement where the stress is greater than 2 squared of F prime C for that particular state of stress in the model under this load combination. So depending on what combination you're looking at, you might get different reinforcement results because of how we're interpreting, number one, the design code that was selected, and number two, what particular combination type you're actually evaluating and looking at. In addition to these combination types, we can also introduce 3 other types. Cracked deflection. For this combination type, the program will check crack deflections in the slab. No code check, the program basically analyzes it. It will give you a result, but it won't design any reinforcement for this combination. And then long-term deflection is used to combine the effects of combinations into a single result. So I'll set this to crack deflection. I'm going to add two combos here. I'm going to add total, and I'll add another one called sustained. And I'll add some factors to these. Total will just be all of the service level load cases, just 1 times service level, and then sustained will be 1 for the dead load, and we'll use 0.3 for the live load. And this combination is really just the same as this one, but they're tagged differently. This is service total, this is cracked. One of them will produce stress checks and reinforcement and so on. The other one is really strictly used only to check for cracking. Okay, and then this one here is identical to this one, but it's used for a different purpose in the set of combinations that we're going to evaluate. And what we'll do next is we're going to add 2 long-term classifications. So we'll say that this is called live load increment, and this one we're going to actually set this to long-term deflection. So the increment is really going to be total minus sustain. If this is cracked and this is cracked less because we have less live load, I want to know what the difference is between the two for live load. That's what we're going to do with live load increment. And I'll take 1 times total minus 1 times sustain. For long-term deflection, in order to predict the long-term portion of this, we're going to use a multiplier. So for our creep factor, we're going to assume that that's 2. So the total long-term deflection will be the instantaneous sustained deflection plus the creep. That equals 3, let's say 3 times sustained plus the incremental live load, which is 1. That's this column right there. And this will be our prediction for the long-term deflection. If we use this button down here, this is just a shortcut way to get a very basic set of combinations with sustained and long-term. If I press this, it says, what's your creep factor? Well, it's 2. I could change it to whatever I want here. I could say it's 3, 4, 5, 1.5. And the program will automatically add that sustained combo, and it will set it to cracked, and then it will take long-term as 3 times sustained, or 1 plus creep factor times sustained. So mine is a little more advanced, not too advanced, but this is just an example of how we can use these different types of tags in the model to build out some combinations for long-term and for crack deflection. Okay, I'll delete those last 2. We already have those basically in the series here. So these are the combinations we will evaluate. Let me go ahead and save the model. We're going to jump down to this. So we've added loads, we've defined combinations. We're going to talk a little more about criteria, and then we're actually going to run the model and do just an initial check for punching shear, just to kind of see where we're at in terms of the punching and whether or not we may have to change the thickness of the slab. And we can also do some prediction on, let's say, the long-term deflection based on the current slab thickness. So in criteria, We've talked about the design code. I'm going to skip over analysis and design options for a moment. Allowable stresses, if we go here, this will dictate for a two-way slab, one-way slab, and beam what our allowable requirements are for post-tensioning and mainly the stresses that are resulting from the combination of the gravity load, self-weight, and also the PT. So here we're working using ACI 318, so our allowable stresses for a two-way slab are shown here for total, and for sustain, these are the tension stresses, top and bottom fiber, and then the compression stresses are 0.45 and 0.6 times F prime C. And for the initial condition, we have our settings here also. So these are based on what's required in the code for a two-way slab. For other design codes that might be European code or British code or just other international design codes, they have obviously different requirements that may not be as strict, let's say, in terms of meeting the target as ACI. For example, with European code, if we set a target and we go beyond that target, then we basically introduce the need for crack control reinforcement, which the program will add. And so it's not as hard as a hard fast rule for other codes it is for this set of settings within ACI. Other options are shear design. We're going to look at punching shear here in a moment. So if I go into shear design, we're going to use shear studs, and the diameter of the stud we'll say is 1/2 inch diameter. By default, the program has number of rails per side set equal, and this is not super conducive to, let's say, a rectangular column. If we have a rectangular column, in order to meet the requirement by code where this distance is less than 2 times effective depth, then 2 rails just isn't going to cut it. We might, need 4 rails, 5 rails. We might even need 3 rails on the short side. So this is somewhat limiting in terms of what it can do for different sizes of columns in your model. In version 2018.1, we have added a few new tools that I think will help with this. Let me go ahead and show these. We've added this option to limit the rails spacing to 2 times effective depth. This is user defined. You could limit it even further if you want, or have less stringent requirements there. But this allows the program to calculate unequal number of rails per side, and it overrides this option here. So that's one new option. Another new option is the option to extend the critical section to the slab edge. And what this means is that if we have a slab edge, let me just grab my other drawing tool here. Let's say we have a corner column. The program checks this distance and this distance. I'll call this X and I'll call this Y. And it determines whether those are greater than or equal to 4 times the slab thickness. If it's less than 4 times slab thickness, then the program in effect will ignore this extension. So the program assumes that the free edge of the column is along this edge of the column and along this edge, and it ignores anything behind here. So for every critical section that you are checking, or that the program is checking, the program is really checking this is critical section 1, this might be critical section 2, and so on. So we're not including this extension, where in reality, if this failed along this critical path, it would have to fail out on the free edge out here. So this option allows the program to actually use this extension. And as a user, you may want to look at the difference. If it's not working by limiting that free edge, and then you come back and you turn this on, it might work. It gives a little bit of guidance to a user as to whether or not it's truly failing, or whether you have more capacity than what the program says per the default setting. So that's new to version 2018. And then also we can provide uniform spacing of studs. This just kind of normalizes the spacing and gives you uniform spacing of studs. So these are the options and the settings that we'll use for the punching shear check. Tendon heights, we're going to talk about this, and rebar requirements as we get further into session 2 on Thursday. So let's go ahead and run this. I'm going to save again. We've modeled the slab, we've added loads, we've gone through a few design settings. Now we're going to jump over here to, we're going to skip tendon and rebar. We don't need to really play with those yet until we get into the design of the strips and after we add post-tensioning or prior to that. We'll go to analysis and we're going to mesh the slab. So I'll use mesh generation. We'll use the simplified meshing option. This is acceptable. We don't need to use the advanced option. That really allows the user to mesh walls with openings. So we don't have any walls with openings in this model. For those of you that don't know, the program can model openings and walls. So if you click on a wall and you go into location openings, you can define openings in this dialog in walls. That's something that was new to Builder 2018.0, and for some of you may be using older versions of the program, so you may not be aware of this feature. We'll go ahead and mesh this. Okay, and once it's meshed, we're going to execute the analysis. And again, our objective here is to look at just an initial look at the deflection and also the punching shear. So we'll run this for all combinations, and where it says apply stiffness uncracked, this just means that the usage case that we're running the program under currently is the default usage, which is called uncracked. It means that we haven't assigned any modifiers to any of the components. Everything is set to 1. So we'll go ahead and run it under that condition. Okay, I'm going to switch over to a top view, and you'll notice we don't want to retain the view of the elements on screen. That can make it a little more difficult to see things in terms of results. So I'll go over to model, or excuse me, I'll go to analysis, and under analysis there's this option for visibility where I can turn the elements off. If they're left on and you just want to use the default display, I don't have shells set to my default, so I can always use that as well. Once the analysis is run, the result display settings will dock over on this right hand side. This is a new browser for result display, and it may look again different than what you're used to, but I think it's more user friendly once you get in front of it and play with it a bit. So the first thing we'll do is select the load combination or envelope of results that we're interested in. And here we're going to just select service total. I'll go to analysis, and under slab deformation, we're going to choose Z translation. Now remember, I have not run the crack deflection check yet, nor the long term. So those don't really apply at this point. I'm just focused on the primary service combinations. And under the loads that we specify, we can see that the deflection out here on this balcony is around 0.85 inches. That's just the linear elastic deflection that has no multipliers assigned to it. There's no prediction of long term in that respect. Now we know we're going to add post-tensioning to this, so it may be a little more difficult depending on experience level whether or not that actually works, because we may have to cram a lot of PT in there to get that deflection into an acceptable range. But within the main body of the slab, you can see this deflection kind of creeps back into this first bay beyond the balcony. So we'll assume that, okay, we're going to live with this deflection for now. If I was to predict long term based on this, I mean, that would be roughly, about 2.5 inches of deflection. But I realize we're going to add PT, and we may be able to add enough PT to limit that displacement. So we'll just say, okay, we're going to continue down the path of 8 inch based on deflection. if we go now and check punching shear, we'll go to floor design, and I'm going to run over here on the left-hand side. We've already set up our shear design options. I'll just go to execute the punching shear. Once I run the punching shear, make sure that you select a strength combination. So under loads again, I'll go to service, or excuse me, to envelope, and we're going to envelope the strength. And back under analysis, there's this new selection tree called punching shear. We'll expand that, and there's some different graphical options here. So we have to reinforce 1, 2, 3, 4, 5, 6 columns. This obviously is considering no post-tensioning, so these results will change again somewhat. This is again just kind of a baseline look at what's happening in the model. So we have 4, 5, 6 columns that we need to introduce reinforcement to. If we look at the stress ratios, we can see ratios for each side separate. So these two are not bad. These ones out here on the interior, these are a little bit more. The condition that the program's checking for those particular columns, if I actually go to a 3D view, this is more user friendly. We're not overlapping the gray with the color below, so that causes the color to be muted somewhat. This is really orange and blue, but because there's gray on top, it makes it more difficult to see. So these are being considered as interior columns along this balcony edge, and these are being considered as interior, and this is a end edge column. So this column and these 4 along this perimeter need reinforcement. Okay, so if we go to reinforcement, the program will show us kind of a shorthand abbreviated form of the rebar. For example, here it shows us the direction, and this is to scale the direction of the rail. This means that you need 11 total rails. You need 3 on the short side, 4 on each long side. That would result, 1, 2, 3, 4, 1, 2, 3, and then 4 here. The studs on each rail are 11 at 3 inches on center. So again, this is an abbreviated way to see what the reinforcement design is for punching shear. This is, for example, a 4-sided rail arrangement, 14 total, 4 and 3 on each side, 5 at 3 inches on center. And then we have the solution for these columns down below. So for this design, we know that with the post-tensioning, we're going to get some relief from the bending and maybe from the vertical force for the direct shear in the column. So we're saying, okay, that these columns, we can live with reinforcing the columns. What we did not want to see was that we were exceeding the maximum allowable shear stress for the column. Now, one thing I failed to do in this model that we want to go back and introduce is I'm going to go back and turn on the CAD file. And one thing I forgot to do is I actually forgot to transform these beams. There's a series of beams along this edge that will help, I think, control some of that deflection. So I'll go ahead and I'll transform those beams. Okay, so those are transformed. I'll turn the CAD file back off. And now I want to set my beam depth and size. So I'll select these beams. I'm modifying a selection again. We'll go back to modify selection. And we're going to change the size of the beam. So I'll select beam. The width of the beam we'll say is a 22 by 24 inch deep beam. Once I introduce a new component to the model, I have to remesh, and to update the results, reanalyze. So we'll do that. We'll go back and I'll remesh the slab. And I'll just update my result by reanalyzing. Now what this will do, having the beam in place, these 4 columns along the balcony will no longer require reinforcement, because now in this case, the program assumes one-way shear controls, and it doesn't check punching shear for columns that are connected to beams. So if we go back and run the punching shear again, we'll just rerun punching shear. I'll go back to my default to turn off the shells, and you can see this says not applicable. These are the only two columns we need for reinforcement. And then for the deflection again, it was 0.85 previous. Now if I go back and update this, I went back and selected service total, and we'll check this on Z direction, and it cut it down to 0.5. And you can see the deflection was along here no longer controls. It's now controlled mainly over on this wing of the balcony. Okay, so that shows an update to the result for a change in the geometry or an addition of a component. Okay, so we're going to stop there for today. Thursday is the part 2. Thursday we're going to set up our design strips and then start modeling the post-tensioning for the slab. We'll model the PT. What we'll likely do is model strips, show an example of modeling the banded tendons and distributed tendons, and we'll advance the model with all tendons and show the process of results and checking stresses, flexural stress, precompression, balance loading, and then final long-term deflections and reinforcement results on this Thursday. I'll go ahead and stop there, and I will entertain any questions you might have. You can, if you don't mind, just enter the question in the chat box, and I'll just wait here and answer any questions. I appreciate everyone's attendance today, and you're free to leave if you have no questions. So thank you. Okay, yes. The question is, the user noticed that we used upper columns in the design. And I'm waiting for the last part of the question, Miriam, so go ahead. Yeah, yes, you can. Usually, when we check the initial stress conditions, it might be more appropriate to check with lower columns only. And then when we check the service total and the service sustained condition, we would check with maybe the upper columns. I think conservatively, you might use lower columns only for everything, but if you wanted to check different combination results per different settings, then what we would need to do really is I would basically take and select my upper components. I could then modify the selection, so I would disregard these components. I'm basically going to ignore them in the run, and in the modify properties I could come here and ignore these columns, and then I would analyze the slab maybe for the initial condition only, this one here, and make sure that this works. If it does, then I would go back, consider these components again, and then rerun the other combinations for those components. So here I'll change those back. And then the second part of the question is, do we consider a release for those components? Well, if you have upper supports, walls, and columns, the default support condition, which is defined in the analysis and design options, the default for single level mode is actually a fixed roller. I failed to talk about this. I should have. This is a fixed roller, and so that means that at the bottom you're releasing the XY translational restraint to allow the slab to shorten. At the top supports, you're actually only fixing it rotationally for X, Y, and Z. So if you disregard these completely, then there's nothing there, and then you only have the bottom supports, which is released in the XY plane. Typically, the columns will still be fixed to the slab, as will the walls under the gravity load condition. If you go and you model this as a multi-story model, and then you add lateral load, then you might want the columns to be leaner only columns. In that case, you would want to release the columns. So it depends on what type of analysis you're running and for the intended purpose. In our case, we're running a single level gravity only PT 2A slab. So in this case, I think it's more appropriate to retain the fixity of the column to the slab. By default, it is fixed. If you double click on any vertical component, column, or wall, and you go to the release tab, you can see here it's actually not released. The user could come in and release it, but that's more of a decision that the user would make based on what objective they have in simulating the analysis or the actual condition for that connection at the time of stressing or in service or whenever you're checking the stresses. Thank you, Miriam. Other questions? Okay, doesn't look like there are any more questions. So I'll go ahead and close for today. Again, thank you, everyone. I'll go ahead and add the video once it's rendered up on our YouTube channel, and we'll look forward to seeing everyone on Thursday. Thank you.